Okay, dear students, let us see what is there in this question. The current I flowing in loop A in a clockwise direction is increasing so as to induce a current both in the loop B as well as C. All three loops are on the same plane. What is the direction of the induced current in the loop B and the loop C? So we are going to comment on the direction of the induced current in the loop B and in the loop C. So my dear students, it would be using couple of laws and you must be very good with it. I tell you in this topic, what is more important? More important is these kind of laws for finding the directions, because they are never going to ask you what is the induction, what is the current flowing in B or C, what is the magnetic field at various places, but they're only concerned with the directions. So be very particular about how to find the directions. Similar topic was in topic 5.4 also. At that time in my playlist, I have shared a video in which I have taught you all the rules with the help of which you can find the direction of the magnetic field, you can find the direction of the forces on the charges, and all those things have been dealt there. But in this topic, we are going to learn about the induction. So the first rule I'm going to tell you is the right hand curl rule. Now, whatever you might call it, screw rule or the right hand screw rule, right hand curl rule, like I'm just keeping my hand like this. So in this kind of laws, what I'm doing in this question, what I'm doing is my fingers are moving in the direction of the current in the ring, and my thumb will be pointing towards the magnetic field generated by the ring. So I'm going to apply this rule on the loop A. So the current is clockwise. So I'm moving my fingers clockwise with respect to me. It should be clockwise with respect to me. So my thumb is pointing towards you. So my thumb is pointing like this. So it is into the page. So I can clearly see that the current is I, and the magnetic field which is created by this current is this. So the magnetic field is into the page, and a very important piece of information is that it is increasing. So first of all, I will write magnetic field which is into the page and it is increasing. Okay, I can also write it here. So this is increasing. Now, if this is increasing, magnetic field is increasing. So let us talk about the loop B. Now, loop B will say that, okay, so there is a magnetic field which is into the page and it is increasing its magnitude, but I do not want it to increase. According to Land's law, every loop will try to go against whatever is the change that you are bringing in initially. So now the magnetic flux is increased with respect to B. So B will say, no, I do not want that. It means that B's induced current will be in such a way that it will try to go against the increase in the magnetic field. So the magnetic field which is into the page is increasing. So we want to have a magnetic field which is out of the page, you see, out of the page. So now my thumb is pointing towards me. So where are my fingers going? My fingers are clearly indicating an anti-clockwise direction. So it means that here we're taking an anti-clockwise direction. This is I dash for the loop B. So definitely loop B will be anti-clockwise like this. Now let us talk about the loop C. So in this loop A, the magnetic field created by loop A, which is actually the initial magnetic field, the source magnetic field due to which all of these things are taking place. So that magnetic field is into the page, but it is into the page only for the points which are inside the loop. But for the point which is outside the loop, let us say this point or this point or this point, if I say, there will be a magnetic field which is out of the plane. Okay, because like this is the loop. So we know that, let us say the magnetic field is going like this. So it's like this. So it will be going like this. So inside it, the magnetic field is having opposite direction, and outside of it, the magnetic field is moving in the other direction. Here, the magnetic field is towards right, and here it is towards left. So accordingly, in the direction of C, for C, we can say that the magnetic field is actually coming out of the page. Be very careful. From the point of view of the loop C, the magnetic field is coming out of the page. So if it is coming out of the page and it is increasing, now C will say, I will not let it increase. So I'm writing it here. The magnetic field is out of the page and it is increasing. So the loop C's induction current, induced current, will be in such a way that it will oppose the increase in the magnetic field which is out of the page. It means that I have to go into this, because now the thumb will be pointing inside, because the magnetic field is out of the page and it is increasing. So the loop says that I do not want it to be increased. So it means that loop C will create a magnetic field which will be into the page. Now into the page means that my fingers are going clockwise. So this direction will be for this. I'm just calling it I2, I double dash. So this is the induced current in C, which is clearly in the clockwise direction, and hence C will be the correct answer. So this is how we do this question, my dear students. And let us see what is the answer given in the mark scheme. I believe it will be definitely C. Well, yes, there it is. You can clearly see, yes, the answer is C. So this is how we do this question. And my dear students, I tell you, these laws for finding the directions, it's very, very important, pertinent for you, that yes, you are very expert in this. You're like, you have to practice as many questions as possible to find the direction of the magnetic field, find the direction of the current, find the direction of forces. It's really very important because these are the only questions that you are going to get in IB. Okay, my dear students, all the best. Bye. Okay, dear students, let us see what is there in this question. The graph below shows the variation with time of the magnetic flux through a coil. So this is basically a flux, and the time here is on the x-axis, which is t. Which of the following gives 3 times for which the magnitude of the induced EMF is maximum? So you want this magnetic field to be, sorry, the induced EMF to be maximum. So by applying the Faraday's law, I know that E will be given by negative of d phi by dt. Again, I'm going into calculus, but this is how we actually write it. But you can write in whatever manner you prefer. So the negative sign only shows the Lenz law, that the induced current will be such that it will be opposing the change that is bringing the induced current in the first place. But we are not concerned with that because we are only concerned with the magnitude here. So we can skip negative sign also. Now, clearly this phi is shown as a variation of sine omega t. It's clear because this is a sinusoidal variation. So I'm going to tell you a couple of methods here. Like I will tell you 2 methods, but the first method is this. So phi is directly proportional to sine, and we know that when we differentiate it, we actually get cos. Definitely there is a negative sign there, and there is there will be omega multiplied the amplitude. We don't care about those things. The only thing is that that will be a cos variation. So cos variation will somewhat look like this. Like this. Clearly, when is the cos maximum? It is at 0, at t by 2, and then at t. So taking these options here, so B seems to be the correct option because it is 0, t by 2, and t. So clearly B will be the right option. So this is the first method that I'm telling you. Like, okay, this is, first of all, this is the sinusoidal variation. You differentiate it, you convert it into cos, and then you can see when is the cos maximum. Accordingly, you have said that, okay, this will be the time when the voltage, the induced voltage will be maximum. So this is the one thing. Now, there is another thing, another way of thinking it. Now, what is the other way? The other way is that clearly E is d phi by dt. So you can say that yes, this pertains to the slope of phi t curve. This is the phi t curve, the flux time curve, and we need to find the slope. So you have to see where the slope is maximum, the induced EMF will be maximum. Clearly, here the slope is 0, it becomes maximum only at 0. And then here it is maximum. Yes, it is in the negative sense, but negative, we do not care about that because we are only concerned with the magnitudes. And the other thing is this. So we can also see only and only slopes if we do not actually want to go into the calculus part of this question. So even then, the answer will be 0, t by 2, and t. So these are the 2 methods in which we can do this question. So my dear students, this is Professor Varun. Thanks for watching. Please share the YouTube channel with all your friends. All the best. Bye. Okay, dear students, let us see what is there in this question. The diagram shows a bar magnet near an aluminum ring. Okay, so this is the aluminum ring here, and this is the bar magnet. The ring is supported so that it is free to move just like a pendulum. The ring is initially at rest. In experiment 1, the magnitude is moved, the magnet is moved towards the ring. This is the experiment number 1. In experiment 2, the magnet is moved away from the ring. in each experiment, what is the initial direction of the motion of the ring? My dear students, there is a concept here, and this is going to be very interesting. Just listen to this. Okay, so when we talk about the induced currents, okay, so we know that whenever there is a change in flux, so EMF is induced and it is given by the formula which is given by Faraday, that is E is equal to d phi by dt. So definitely when we are moving this magnet to and fro, there is a change in the magnetic flux associated with the ring. Now, the flux linked with the ring is changing, and due to which there will be an induced EMF, and definitely there will be a resistance of the ring, so there will be an induced current also. So the induced current will be given by E divided by R, so there will be this induced current that will start flowing in this. Now, up to this, that is fine, and you can be asked the question like how the current, what will be the direction of the current, and how the current will be induced, and all those kind of questions. They can be solved easily. But in this question, he's talking about the force that is acting on the ring. Now, the big question is why there will be a force on the ring. But I will be telling you that. First of all, let us answer this question. Now, we are going to use the Lenz's law. Now, in Lenz's law says that the ring will try its best to nullify the initial effect that is brought into initially. Like, for example, the magnet is moving towards the ring and the flux has increased. So the ring would be saying, I don't want the change. So I will stand against the increase in the flux. So how the ring is actually going to achieve that? How do you think ring would be doing it? Number one, it would be inducing a current and it will create its own magnetic field, and that magnetic field will be opposing the additional magnetic field that was increased, thereby reducing the magnetic field, thereby reducing the flux. But there is another method. The another method is to increase the distance between the two. So it will be a humble attempt by the ring to move away from the ring, to increase the distance so that the bar magnet is coming near to it. So ring will try to move away from it because it does not want the flux to increase. So that becomes another method chosen by the ring so that the flux does not increase. So definitely in the first experiment, it would be moving to the left. Now, we are going to apply the same principle for the other direction in the experiment 2. Now, in experiment 2, the magnet is now moved away from the ring. Obviously, the ring will be witnessing decrease in the flux, and the ring will say, I don't want it. So now the ring does not want the flux to decrease. So what can ring do? So ring will be creating an induced current which will create a magnetic field that is going to supplement the initial magnetic field which was reducing. So if this is the north pole, let us say the magnetic field will be towards this. So current will be in such a way that the magnetic field, induced magnetic field, will be towards the left side. But the second part also we have, now the ring can also do this thing, that the ring will start moving towards right. Why to right? Because now the magnet is moving towards right hand side, it is moving away. So the ring will say that don't go there, don't go there, don't do that. So ring will try to come near to that. Okay, so it means that ring is now going towards the right hand side. So definitely our answer is going to be B, no doubt about that. So this is the explanation for this complete question. But now there is another question, and the question is, why is the force created on the ring? Like I've given you all of the phenomena, but is there any why? Like induced current is understandable, but force, we have never even considered the force earlier. So how can we explain that? Yeah, I tell you. See, when we have this kind of a motion going on there, this ring acts like a magnet. So this ring, like I'm going to show the ring like this, let us say. Yeah. So this ring is having two phases now. So one face is going to act like north face, another face will act like a south face. Let us say there is an induced current, and induced current is creating a magnetic field of this direction. Clearly it means that magnetic field is moving like this. And so what about the magnetic faces now? So this is one face and the magnetic field is coming out. So the face that I'm showing is the north face, and the face which is behind that will be acting like the south face, because magnetic field lines, they're entering into the ring from backside. It means this is the south face, this is the north face. So these are the two faces. Now these two faces, because of these two faces, I can say that ring is actually no longer acting like a ring, it is now acting like a magnet. So it itself has converted itself into a magnet, thereby creating the forces of attraction and repulsion uh, in regards to the other magnet. So in one case, there will be a south face here, so it will start attracting. And in another case, there will be a north face on this side and south on the other side, and it will start repelling. So these two things can happen. So I've just tried to describe the concept behind this, like what is actually happening. You have to understand this thing by yourself. Now try to do this question once again, watch the video again, and this concept will be crystal clear. Okay, my dear students, this is Professor Varun. So I think the answer is given, so this is it. Thanks for watching the video. Please share the video with your friends. All the best. Bye. Okay, dear students, let us see what is there in this question now. What are the units of magnetic flux and magnetic field strength? So, okay, so it's a bit straightforward question, I would say. See, magnetic field strength. It has many names, I tell you. Magnetic field strength. It is also known as magnetic field intensity. It is also known as magnetic flux density. So do not get confused if you're having these three names. They are actually talking about physical quantity which is denoted with B. So this is actually the corresponding thing in the magnetic field for electric field intensity, isn't it? We just write E for the electric field intensity. Similarly, we write B for the magnetic field intensity. And the unit for this is clearly Tesla. Well, it has nothing to do with Elon Musk, by the way. Do not get confused. That is just a company by the name Tesla. This is about Nikola Tesla, the scientist, and he is just like, um, what can I say? So we have a unit by his name, that is Tesla. So this is the magnetic field B. And he's talking about the magnetic flux also. Now, what is this flux? So magnetic flux is completely a different game. Magnetic flux. Magnetic flux is B into A. B into A. It is the product of magnetic field and the area of the loop or whatever you are talking about. So definitely this is Tesla. This is meter square. So the SI unit for the magnetic flux will be Tesla meter square, which again is given a new name. Like there is a scientist known as Weber. So they have given, like, just out of respect, they started calling this thing as Weber. Okay, and the unit for the magnetic field intensity is Tesla. So in this question, for the magnetic flux, we are going to say Weber, and for the magnetic field strength, it will be Tesla. So definitely the answer is going to be B, no doubt about that. So why I am doing this question in that much detail? Because you are time and again going to get this question from the electric field as well as from the magnetic field. So the topic 5 point, so that all the topics in 5 and all the topic related to 11, topic 11, units are really very important for these two topics. Like IB would be asking you questions, and that will be from the topic number 1, but that would be actually from the topic 5 and topic 11. Like for example, if I ask you what are the units of electric field intensity, what is the unit of capacitance, what is the unit of magnetic flux, and what is the difference between magnetic flux and magnetic flux density, just to confuse students. So there is a high chance that you can get confused. So be very careful in the topic 5 and topic 11 in regards to units. Also, let me tell you one thing. This Tesla, like now I can clearly say that Tesla meter square is equal to Weber. So this Tesla can also be written as Weber meter negative 2. So Weber meter negative 2 is also available here in the options. Do you see that? So even this option is correct as per the magnetic field strength is concerned, because Tesla is actually same as this. Got it. So we have to be very careful. Accordingly, Weber can be written as Tesla meter square also. So they are using Tesla meter -2 here, but it could be written as Tesla meter square also. So be very careful with these kind of questions. And this is how we do this. By the way, in this question, they have not done anything mischievous, only a straightforward answer, that is B is given. So my dear students, be very careful. It's simple question, but still it has many complexities involved. Okay, my dear students, this is Professor Varun. Please share the video with all your friends. Also, join the YouTube channel to access the paper 2 questions. All the best. Bye. Okay, dear students, let us see what is there in this question now. A plane of a coil is positioned at right angles to a magnetic field of the flux density B. The coil has n number of turns and each of area A. The coil is rotated through 180-degree in time t. What is the magnitude of the induced EMF? Okay, dear students, so what we do in these kind of questions, I tell you, according to Faraday, E is given by the change in flux divided by change in time. Well, when I use the calculus terms, it is always about the instantaneous values of the EMF that is induced. So this is the instantaneous value, like you are moving and instantaneously at every instant, what is the EMF that is induced. But we are not concerned with that now, because he's saying that it is rotated about 180 degrees in the time t. So we are just concerned with the initial and the final position. So we are indeed talking about the average value of the EMF induced, and that will be given by change in flux divided by change in time. My dear students, be careful. I'm not using any negative sign there, because negative sign wants to talk about the direction of the induced current and the induced EMF, but that is of no objective here. That is why I'm not including the negative sign in the first place. So what is happening here is we are going to find the first flux. So first flux, the area is like this. So the magnetic field is towards left hand side. So I will say that the direction of the area is also towards left hand side. So the flux can be taken as B into A. Now one side will be taken positive, another will be taken negative. So you can choose the right hand side to be positive, left hand side to be positive, anything. In this case, because a magnetic field is towards left hand side, I just take the left hand side to be positive. So this side will be positive. Now what is phi 2? And obviously there will be cos theta. Cos theta. Now there is a problem. What is the theta here? You see, they say that the plane is at right angles to the magnetic field. So it's highly susceptible here, or I can say deceptive here, that students will be taking angle to be 90 degree. But no, this is not 90 degree. The angle is 0 degree. You see, the plane is at 90 degree with the magnetic field. The plane of the coil is at 90 degree, but we are not concerned with the plane of the coil. We are concerned with the area as a vector. Yes, area is a vector. Now, I'm concerned with area vector. So this is, let us say, the loop here, and it's drawn like this. So you now know like which phase is like here and which phase is on the other side of the diagram. So let us say we are concerned with this area, this area. So this will be the area vector. So we can say that, yeah, this is the plane of the area. Try to understand. This is the plane of the area, and the magnetic field is given by, let us say, magnetic field is also in this direction. So in this case, clearly the magnetic field is perpendicular to the area of coil, but magnetic field vector is parallel to area vector. We are actually concerned with the area vector. So do not be fascinated with this thing when you read, no, like right angles, and eventually you just jump to the conclusion that theta is 90 degree. Theta is not 90 degree, it is 0 degree. So for this case, it is 0 degree. So here I'm just substituting it to be 0. So cos 0 is 1. So clearly this is equal to BA. Now let us go for phi 2. Now what is phi 2? It will be BA cos 180 degree. Why? Because you have now rotated it with 180 degrees. It means that now the ring is like this. Now area vector is in the backside direction, but the magnetic field is still in the same direction. So what is the angle between the magnetic field and area? 180 degree now. So this will be 180, and cos 180 is negative 1, so it will be negative BA. Now obviously there are n number of turns, so all of the flux will be multiplied by n, so this is becoming NBA, and this will also be negative NBA. Now I want to find the change in flux, so it will be final minus initial, so negative NBA negative positive of NBA. So overall it is becoming double the NBA. Definitely we are not concerned with the negative sign, so we can get rid of it later. Don't worry about that. So the delta phi is twice of NBA. Now what is the time taken? Time taken is T. So clearly the EMF induced is twice of NBA divided by T. So it is twice of BAN divided by T. So definitely D is our correct answer. So this is how we do this question, my dear students. This is a repeat telecast question, finding the average EMF. This is average EMF because we are only concerned with the initial position and the final position, not in between them. So this question is to be done like this. This is a very important question. Please watch videos again and again and try to be perfect with this question, because I know you're going to get a similar question there in your examination. Okay, so my dear students, this is Professor Varun. Thanks for watching the video. Please share the YouTube channel with all your friends. Please try to join the YouTube channel if you want to access the paper 2 questions, which are as explanatory as paper 1 answers here that I'm giving. All the best. Bye. Dear students, let us see what is there in this question now. A magnet connected to a spring oscillates above a solenoid with a 240-turn coil as shown. The graph below shows the variation with time t of the EMF across the solenoid with the time period t of the system shown. It means that the graph is already talking about the induced EMF. So we are no longer talking about what is the induced EMF, what are the formulations and all that. So the graph is already given. Okay, let us see what is the question now. The spring is now replaced with one that allows the magnet to oscillate with a higher frequency. So frequency has been increased, which graph shows the variation with time t of the current I in the resistor for the new setup. So my dear students, reading this question, like I can just say that it's quite weird, because this kind of a theory or this kind of a topic is not in our syllabus, not in your syllabus. In fact, it is like, even I have not seen this kind of thing even in Indian books. Because why I'm saying Indian books, because in our syllabus, like our syllabus is very big, that is why. So this is a very peculiar question, a very different question, and it is employing the magnetic field created by the bar magnet. Now that is not there. Magnetic field created by current carrying conductor is there in our syllabus, but magnetic field created by bar magnet, that is not actually in our syllabus, isn't it? So one thing is clear, that we need not to go into very much details into the question, because it is clearly out of syllabus question kind of thing. But let us see if we are able to see this thing or not. Now the one piece of information that is given here is that the frequency has increased. So if the frequency has increased, doesn't it actually mean that the time period has decreased? So if the time period has decreased, so we can say, like, for the one oscillation, yeah, in the option A, the time period has decreased from what it was earlier. In this case, the time period is the same. In this case, the time period is the same. In this case, the time period is shown to be increasing. Sorry. In this, in this also, the time period is lesser. My mistake. The time period is lesser. But now try to understand. Here they have shown that, okay, so first of all, B is wrong and C is wrong. Now only and only the answer is between either A or D. But we have to see what this I naught value is. So I naught value, yeah. Here you see this is the V naught value. So corresponding value to this has been taken as I naught. Okay, so in this case, whatever was I naught, whether it was lesser or whether it was more something, whatever it was I naught. So in the new case, when the frequency is bigger, the amplitude of the current has increased. So you see, the amplitude of current is increasing in this, and in the option D, the amplitude of current is not increasing. But as per my knowledge, whenever the frequency increases, the magnitude of the EMF induced is also increased. Why? Because if the frequency has increased, clearly the time period is lesser. Clearly, it means that the velocity with which the spring is moving has increased. Clearly, the velocity of the magnet has increased. And it is the experiment given by Faraday that more is the velocity, more is the rate at which the flux is changing, more is the EMF induced. So clearly, if you are decreasing the frequency, there has to be a relationship that will say that yes, the amplitude of the current is now going to increase. So there are two informations that are required. Number one, the time period should be lesser than the previous one. And number two, the amplitude of the current should be bigger than the amplitude of the current which it was in the initial case. That is why we can clearly say that yes, the answer will be A. One thing is very clear about this question, my dear students. Please understand this. This topic is not in our syllabus. It is not given in the book. It is not given anywhere. The formulas related to this are not given in the data booklet, because this is actually not the magnetic field created by the current carrying conductor. It is a magnetic field created by a Bohr magnet, and that is not in our syllabus. Okay, dear students, this is Professor Varun. I think things will be very clear. I will show you the mark scheme, whether the answer is A or not, but I'm sure the answer should be A. And yes, clearly you can see here the answer is given as A. My dear students, I have already started uploading the paper 2 questions. Paper 2 questions. So please join the YouTube channel if you want to access those paper 2 questions. All the best. Bye. Okay, dear students, let us see what is there in this question. Two identical circular coils are placed one below the other so that their planes are both horizontal. So be very careful about the statement, because there are students, I have done this question with a couple of my students. They were highly confused, like what the hell is happening here. Try to see, these are the two different planes, like these are horizontal planes, and these coils are perfectly circular, but because they are like this, so they're not looking circular, they're looking oval. I'm going to draw this something on it, and things will become even more clear. Top coil is connected to a cell and a switch. The switch is closed and then opened. What is the force between the coils when switch is closing and when switch is opening? Again, the question is about the forces, and the question is not about the direction of the induced current. It is about the forces. So in a couple of previous videos, I have described each and everything about the forces, but even now I would be doing the same. Do not worry about that. First of all, let us make this diagram more sensible. You see, I'm going to draw these lines here. So that the plane in which they are, yeah, do you see this? So the planes become clear to you like this. Like this. So these two lines are actually not required. I just drew it. Okay, like this. Okay. Now you see, so these two are placed one above other. Now the switch is closed. So when the switch is closed, it means that current will start moving into the circuit. So earlier the current was 0, and now after some time the current will become I. So current is increasing. So current is increasing. This side is positive, this side is negative for the battery. So the current is going like this. And so I'm now using my curl rule. So the magnetic field is in the upward direction. It means, yeah, clearly, because this side is outside. This side is actually outside of the screen. This side is at the back side of the screen. Be very careful. So we are using hand like this. And so I can say that the magnetic field produced will be in the upward direction. So how the magnetic field will look like? It will look like this. Yeah, like this. So this is a magnetic field that is now going up, just like a fountain or something like that, isn't it? So it is coming out like this. So now when it is coming out, we can say now With respect to the second loop, what I'm saying is that the magnetic field is in the upward direction and it is increasing. So obviously the loop is going against it, so loop does not want that to happen. So there are two methods in which this can be achieved. Either the loop can give rise to an induced current in such a way that the magnetic field which will be produced by the induced current will be in opposition to the upward magnetic field. It means that the induced current in the second coil will be in the other direction, so that the magnetic field produced is downwards. So what will be the direction of the current here? Let me show you this. So in this loop, yeah, the current direction will be opposite, like this, like this. So the current direction will be like this, so that a new magnetic field is created which is downwards, and this magnetic field is going to oppose that. Well, that is only for the induction current, but we are here not supposed to find the direction of induction current. We are here to understand the forces. Try to understand now. Because the flux is increasing, the second ring will try to push the above ring. So there is only one method in which the flux can be reduced, by increasing the gap between the two. So this ring will try to create a repulsive force while the current is increasing. So when the switch is closing, so the forces have to be repulsive. Clear? So forces have to be repulsive so that the distance between the rings increase, and thereby reducing the flux, nullifying the effect of increase in the current. Now, let us say that switch is opening. Now, when the switch is opening, I will say the current was I and it is now becoming zero. So now it is the other way around. Other way around means that now the current is reducing in the above ring. The diagram will be the same. Clearly, you can see that, okay, the magnetic field will be in the upward direction, but now the magnetic field will be decreasing. Now, if that decreases, the ring will say that no, the induction current has to be in the same direction. So these directions will be reversed. So the directions now, they will become like this. And the magnetic field which is produced will also change. So magnetic field will be in the upward direction. Well, this much is only if you want to find the direction of the induced current, but that is not the question. The question is, what will be the force? Now you see the flux is decreasing. So the ring will say, please do not decrease the flux. Ring is always going to oppose the initial change. So how is that possible that the flux is not reducing? They will start attracting each other. So the downward ring and the upward ring will be having an attractive force. So that will be attractive, and hence the answer for this question will be C. So my dear students, this is how we do this question. I believe I have addressed all of the issues. We have talked about the induced current also. So you will not be facing any much problem in this question anymore. Okay, my dear students, so this is Professor Varun. Thanks for joining. And please share the YouTube channel with all your friends. You can now join the YouTube channel if you want to access the paper 2 questions. All the best. Bye. Okay, dear students, let us see what is there in this question now. A coil is rotated in a uniform magnetic field and alternating EMF is induced in the coil. What is a possible phase relationship between the magnetic flux and the induced EMF? So we know the mathematical relationship. E is equal to negative of d phi by dt when the variation of both quantities are plotted with time. And they're literally talking about phase relationship. So we are not going to neglect the negative sign now. Obviously, we have to take care of that. Okay. Now, so the flux, if the flux is BA cos theta, sorry, and we need to differentiate it. So the cos will become sine and there will be a negative sign. So this is what we need to understand. Now, let us see. First of all, what is the variation of the flux that is given here? Is it cos or is it sine? So you see here, the magnetic flux is shown in the dotted line. So this is sinusoidal, this is sinusoidal, this is sinusoidal. So in majority of cases, it is sinusoidal. So we are going to say that the flux is directly proportional to sine theta. Now, obviously, the EMF that will be produced, we have to differentiate sine theta. So that will be cos. So it will be directly proportional to cos, but there is a negative sign also. So the EMF induced now will be having will be having a formation of a negative cosine graph. So let us see. So it is not in A. Well, it is such is the case in the B. You see, this is the magnetic flux, and which is definitely a sine theta variation, and in place of theta we can also write omega t, to be very particular, because on y-axis on x-axis it is t. So the EMF that is produced, it is clearly the negative cos omega t variation. So this is going to be the phase relation between the EMF and the sine omega t. So there's no doubt about that. So B should be the correct answer. But let us see the other options also. So I'm erasing this all. But for me, I believe B will be the correct answer. See, in C, okay, and in D, let us see. So let us go for D now. So in D, the flux is again sine omega t, but the EMF is negative sine omega t. So this is wrong because it has to be negative cos. Here, this is sine omega t and this is actually cos omega t positive, but it will not be positive, it will be negative. So I believe we have to include negative here. So if I was sitting in the examination, I would be going with B. Let us see what is the mark scheme. Yes, the answer is B for this question according to the mark scheme. So this is how we do this question, my dear student. And this is Professor Varun. Thanks for joining. Please share the YouTube channel with all your friends. Now you can even join the YouTube channel if you want to access the paper 2 questions. I am in process of uploading them and you can access them by joining the YouTube channel. The link is there down in the description box. All the best. Bye. Okay, dear students, let us see what is there in this question. A conducting square coil is placed in a region where there is a uniform magnetic field. The magnetic field is directed into the page. There is a clockwise current in the coil. What is a correct force that acts on a side of the coil? Okay, fine, no problem. So all of the options A, B, C, D, they are showing the direction of the force on that wire. Sorry for that. Yeah, so A, B, C, D are the forces that are acting on the wire, and the current is moving in the clockwise direction like this. So we want to find the direction of the force. So as I have already told you that I am using right hand palm rule type 2 for this. Try to understand right hand palm rule is like it's quite common and people understand what right hand palm rule is. Majority of like teachers would be aware of what this is, but I always prefer using this instead of using the Fleming's right hand rule and the Fleming's left hand rule. I do not use those rules. I use right hand palm rule. And for this, finding the force on a positive charge, finding the force on an electron, finding the force on a current carrying conductor, I use right hand palm rule type 2. So I just call it type 2. So I have given the complete description of type 1, type 2 and all that in a video which is already present there, and I think you can find that video in the playlist 5.4 and you have to search for it. I will see it and I will mention the link also, but you have to see that to properly understand what is a type 1 and what is type 2. So here I am going to apply the type 2 rule. I'm going to use the right hand palm rule. So I keep it like this and my fingers will be pointing towards the magnetic field. So magnetic field is into the page. So my fingers are now pointing into the page and my thumb will be pointing towards the current in the wire. So if I'm talking about the C part of the loop, let us say, so the current is downwards and the magnetic field is inwards. So where is my palm? My palm is pointing towards right hand side. It means that C will be experiencing a force in the right hand side. So C direction is definitely wrong. Similarly, we are going to apply this rule for all of this. I'm going to write it here. Fingers will be pointing towards the magnetic field. Thumb will be pointing towards the current and palm will be giving you the force which is on the current carrying wire. And you must also be knowing about the magnitude for this. It is BIL, Bill. Yeah, BIL is the magnitude of the force, but we need not to find that. Anyways, just given for keep that thing in your mind. Now let us go for A, B, and C and D. All of that. Let us go for D now. So the magnetic field is into the page and the current is going towards the left hand side. Definitely the palm is pointing downwards and the D direction is showing downwards. It means that yes, this is the force there. So no doubt about that. D option is definitely correct. Definitely then it means that A and B are going to be wrong. So, my dear students, this is how we do this question. Okay, so this is how we do it, and the answer for this question is D. My dear students, I have started uploading the paper 2 questions also, so you can join the YouTube channel to access those paper 2 questions. Description is given in the description box. All the best. Bye. Okay, dear students, so this is let us see how to do this question. X and Y are two plane coils parallel to each other that have a common axis. There is a constant direct current in Y. So in Y there is a direct current going on and the direction is also shown there. X is first moved towards Y, later it is moved away from Y. What, as X moves, is the direction of the current in X relative to that in Y? Okay, so the options are given like same direction as in Y, opposite direction as in Y. Okay, so my dear student, first of all, in these kind of questions, the first thing that you must understand, the first thing that you must look forward to is this line, the central line that is drawn here. Many a times I have seen, and you might have also seen, the rings are drawn like this, and there is no line there. This becomes really very difficult. Line has to be drawn. So if there is no line, you are supposed to draw the line by yourself. But in my point of view, until the line is there is no guarantee that you would be able to answer it properly. So there has to be this line. You have to draw this. Like we have drawn this line now. Clearly, this end of the ring is behind the screen, and this end of the ring is actually in front of the screen. Because this is a 3D diagram that we have to draw on a 2D plane. That is why these kind of problems are faced. But it is very important for us to understand how is the ring actually placed. So this is how it is placed now. Clear? So the current is shown here. It means that from this point of view, like let us say this is an eye. Forgive my drawings that I'm drawing there. So let us say you are watching from that side. So if you're watching from that side, the current is clockwise. So current is clockwise from this side. It is anti-clockwise from this side. From this side it is anti-clockwise, but from this eye point of view it is clockwise. So whenever we say clockwise and anti-clockwise, we have to say what is your reference point. But anyways, we have just seen that, okay, fine, the current is going like this. Now the current is going like this. So how is the magnetic field there? And we have to draw that. So I am applying my right hand curl rule. So the current is going into the screen like this, and so the magnetic field will be towards left. So this is the actual direction of the magnetic field. Like this. So the magnetic field is drawn like this, and it is drawn into the wire, and it is going like this. So it means as per X is concerned, this is the direction of the magnetic field. We are going to study this question from the point of view of X, isn't it? Now, X is now moving towards Y. So now X is moving towards Y. So if it moves towards Y, the distance is coming near. It means that flux is going to increase because now the distance will be lesser. Now the flux is increasing. So X will say that I do not want it to be increased. So point number 1, it will apply a force which is repulsive. A repulsive force will come into play and X will start repelling Y because it actually does not want to go near to Y. But it has to. So we are moving it near to Y, but there is a repulsive force. But the question is about the induced current. So now concentrate here. So to find the direction of the induced current, we will see that, okay, fine, the magnetic field is towards left and it is increasing. And it is increasing. So the ring X will say, do something to reduce it. So what will happen? Obviously, there is a repulsive force, but there will be a second thing also. It will try to create an induction current, which will create a magnetic field in the opposite direction. So it means that I am going to use my hand like this. Now you see the magnetic field has to be towards right hand side, so I'm curling my hands like this. It means that current should come out of the screen from the top end. It means that clearly the current is now moving in the opposite direction with respect to the current in the Y. So this will happen and a magnetic field will be created in the opposite direction, so that this magnetic field can fight the corresponding increase in the magnetic field in the left hand side. So that is why we have to counter that. That is why I can say that yes, in the case number one, the current will be in the opposite direction. Now let us go for this one. Now, so in the second case, X is moving away from Y. Now it is moving away from Y. Obviously, the whole process will be repeated, and you can clearly see that current will be in the same direction. So now the current will be in the same direction. And so the answer for this question is definitely going to be C. So for the second part, you have to do it by yourself and try to verify if you are also getting the same answer. So my dear student, this is how we do this question. These kind of questions are really very important. Either they ask you questions on the forces between these two. So in this case, when X is moving towards, there is a repulsive force here. I'm just writing. And here they will start attracting because now they are going farther away. So X will say, no, 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 I don't want to go farther away. I want to maintain my position. So now there will be an attractive force between the two rings. So my dear students, either they would be asking you question based on forces, or they will ask you question based on the direction of the induced current. But this is how we are going to do it. My dear student, this is Professor Varun. Thanks for joining. Please subscribe to the YouTube channel. Also, please join this YouTube channel if you want to access the paper 2 questions. All the best. Bye.